Hello everyone. Today we will be using PyTorch to make a simple neural network. I will first go over all the theories behind, and then we will dive deep into the application using the PyTorch code. The task we are trying to deal with is known as a classification problem, which is a subset of tasks under the large category of supervised learning. In a classification problem, the data is put into different classes, and our neural network needs to predict the class that the data belongs to. Our AI is trained using many example instances of our classification problem, which are all labeled by a human. Since the man-made labels of the data guide the training process, we call this supervised learning. A simple neural network consists of input layers, hidden layers, and output layers. At every neuron, information is collected from previous connections, multiplied by a weight value, and then the bias is added to it. The weight and biases values are adjustable and are made to fit our data better, so they are known as trainable parameters. After that, a nonlinear function is applied to each neuron's value, giving an activation value. Such a nonlinear function could be the ReLU function or the sigmoid function. The information then passes from the first layer to the second layer down to the last layer, and it is the output of the model. For a classification problem, the output values are then normalized using the softmax function to output the probability which predicts each class. To train the neural network, the prediction of the model is compared with the actual labels. The difference in predicted values will create a loss value, which we can calculate using the cross-entropy loss function formula. After that, we would like to adjust the parameters of our neural network to reduce the loss. This can be done by gradient descent, which uses multivariable calculus to calculate the gradient of each weight, which is the amount of change that needs to be applied to each parameter in order to reduce the loss. For more information on gradient descent and backpropagation, you can watch the video on it by 3Blue1Brown. In actual machine learning, we sample the training data in large batches and do the loss calculations for each batch. This will help the training process by setting the objective of the gradient descent to minimize the average loss among all samples, instead of fitting the model to one single data point. We can also decide the number of times that the data is used to train the model, which is known as the number of epochs. And also we can decide the learning rate of our gradient descent algorithm. We will also need to test our model with a separate testing dataset, which will help us make sure that the model does not overfit, which means that our model could work very well for the training data, but it may generalize poorly for unseen data. By having a test dataset, we can validate our model to see if it is also accurate when applied to the testing dataset. Now we will create a new Jupyter notebook to put our PyTorch code. And for this tutorial, we will be needing PyTorch and Torch Vision installed in order to run the code. To check if it is installed, we can open our command prompt and do pip show torch and pip show Torch Vision. You can also use other methods to install PyTorch and Torch Vision, and also you can run your code inside Anaconda. For my computer, I will be running PyTorch with the GPU version, but it is okay to use the CPU version. Now let's import all the necessary code. For our tutorial, we will be using the fashion MNIST dataset. Then let's take a look at what kind of information the training data contains. We see that every instance of a training data is a tuple, and the first entry of the tuple is a tensor containing the data for the individual pixels of our image. And the second entry of our tuple is a number, which is the label for our data. Let's take a look at the first entry. And we can see that the shape of our every training data is of this very specific size. So we can also try to print out the data and take a look at it as an image. To do so, we will need the library called matplotlib. Since our image needs to be a 2D image, and however our training data is a 3D tensor, we will reshape the training data into this shape, and then we can plot it using the image show function. The color map used is the gray one, but we can also change it to reverse the colors, which gives this image of a boot. So with a better understanding of our training data, let's take a look at the actual details we need. First, we need to set up our device, and the standard way to do so is this is the standard way to set up the device used for training, which is either the CUDA or the CPU. If you have the GPU version installed, you should see CUDA here, and if you have the CPU version installed, you should see CPU. For most cases, using a graphics card will be faster than the CPU, but since our task today is relatively simple, it's okay to use either of these devices. Next, we will set up the hyperparameters. And then now we need to put our data into individual batches. The way to do so in PyTorch is by using a data loader. Now with the preparation completed, we can now start defining our model for the neural network. Our neural network will have input layer, 2 hidden layers, and then output layer. The hidden layers will have 64 neurons each, but if you view it as PyTorch parameters, it is actually 3 separate matrices of different sizes. And then we need to write down the logic for a forward pass. Our model will first flatten the input image into a 1D tensor, pass through it a linear layer, perform ReLU, linear layer again, ReLU again, and then a third linear layer. The results outputted by a linear layer will range from -infinity to infinity. So since we are trying to output a classification, which is a probability, these are actually logits. So this will be our model. To make sure our model is correct, we can print it out. Next, we will need to define a training and testing loop. And of course, we will need to define a training function and a testing function. The training function's logic is basically it takes each batch, calculates a forward pass, and then performs backpropagation to update the weights of our neural network. We perform this using all the batches in our data loader, and that will be one epoch. When the x and y's are loaded from the data loader, they are automatically in our CPU, and we need to move them into our GPU's graphics card's memory. So the x.to device performs this action. We can call our model just like a function and use x as our input. Next, we calculate the loss between the prediction and the actual values y. And then we perform backpropagation using these three simple steps. The first step resets the gradients that we have for the trainable weights. The second step calculates the gradients backwards. That comes from the loss function calculation. And the last step changes the parameters according to the weights calculated by the gradient function. This is our very simple loop, and we forgot to write down the loss function and the optimizer. For the loss function, it will be using cross entropy. And our optimizer, for this step, we will use stochastic gradient descent. Now, we want to improve our training function to output more information about the current training progress. One of the following ways is to, for every 100 batches or so, output the current loss. To do so, we need to apply the enumerate function to our data loader. So instead of only looping over x and y, it also outputs the current index I, or the current time step I. Since the loss variable is a tensor, we need to convert it into a number using the dot item. And this will show the current loss. We also want to output the number of batches that has already been handled. So this should be it. As you can see, our model is training, and the training loss is decreasing quickly. And we want to, since we do not want our model to overfit to the training data, we also need to perform a test at the end of every epoch. The test function will be very similar to our train function, and it passes the testing data into our model, and it outputs the loss calculated using the testing data. One thing that we forgot to do for the training data is to set it to with the training function is to set the model to training mode, and the eval will set the model to evaluation mode. This is necessary because evaluation mode means that the model's gradient will not be calculated, but the gradients will be calculated in training mode. For our testing data, we are interested in counting the percentage of correct predictions done. So this line chooses the largest probability predicted by our model and checks if it is equal to our training data y. Since we are comparing two tensors, this will create a tensor of booleans, that is true or false values. We convert the booleans into floats and add them together, which will output the number of equal predictions, and that will be our correct value. I mean the value for correct. Now to show the testing, we need to reset our model since we have already trained our model once, and we will start the notebook from this line. As you can see, the accuracy of our model is improving for the test data. This shows that it did not overfit and it is doing a good job at predicting. Now to apply our newly trained model, let's see if it can make a correct prediction when we apply it to the training data images individually. The y-hat variable is the prediction made by our model, and you can see that the predicted probabilities are here. And if we take the maximum, it would be in class number 9. And let's check if class number 9 corresponds to the same class as our original boot. As you can see here, our original training data is also in class number 9, which shows that our model has done the prediction correctly. Let's try it for other training data. We see that for this long code, our model also did the prediction correctly. We should expect that our model should have an accuracy of around 82% or higher, since we are dealing with the training data here. Now for the last part, let's take a look at which part of the code we are allowed to modify. For example, instead of the fashion MNIST data, we can work with the original MNIST data set, which is the set of images that contains handwritten digits. For example, this is 5 here, and running the code again, it should work since our training data is the same size, or the same shape. Our model predicts that this handwritten digit here is a 2, which is correct. Now, other things that you can try and configure is, for example, the optimizer used. Stochastic gradient descent is a relatively slow optimizer. A faster optimizer would be like Adam. As you can see here, the loss jumps from 2.3 down to 0.3 in just 100 batches, and Adam is really a faster optimizer. Other things that you can configure are like the hyperparameters. You can try different batch sizes, learning rates, etc. And this will be it. And I hope that this video shows how easy it is to learn machine learning, especially for some very simple applications. I hope you like this video, and if you do, make sure you like, subscribe, and stay tuned as I will be uploading more videos about machine learning in the future. Thank you, everyone.